So we've seen two examples of set union. The first one had no overlap between the sets A and B. The second one had a partial overlap between the sets A and B. Now let's look at an example where we have a set A and we have another set B which is a proper subset of A. So let's say that the set A is the set of vowels. So we have represented the vowels by these 5 points here, and the set B is a subset of A having the vowels A, U and I. So E and O are outside of B but still within A. So what would be the union of A and B? It would be the set A itself. So when the set B is a subset of A, then their union, the union of A and B, will be the set A itself. Because by taking the union, we don't add any extra elements, since every element of B was already present in A. So the union of A and B will just be the elements that are in A. Now it should also be obvious to you that if we take the union of A with itself, this will also be just the set A. If we take the union of A with the empty set, this would be the set of elements which belong either to A or to the empty set. Now there are no elements in the empty set, so this will just be the set A. This is like saying that if you take a number and add 0 to it, it's not going to change the value of the number because you're not really adding anything to this number. Also note that it doesn't matter whether we write the union as A union B or whether we write it as B union A. The order doesn't matter, the order in which you write the sets. So A union B is the same as B union A. We are just merging together the elements of both the sets, and it doesn't matter in what order we write the sets. Now the union operation can also be extended to multiple sets. For example, if we had 3 sets A, B and C, we could take the union of all 3 of them, and this would be the set of all elements X such that X belongs to A, or X belongs to B, or X belongs to C. Of course, X could belong to more than one of these sets, but for X to be present, for any number or for any element to be present in the union, it has to be present in at least one of these sets. So in this Venn diagram here, the union of A, B and C would be represented by this shaded region. So again, it doesn't matter in what order you write these sets. You could have written this as B union A union C, or while evaluating what the union is, we could first take the union of B and C and then take the result and add the elements of A to the result, or we could have first calculated what the set A union B will be and then add the elements of C to that result. It doesn't matter in what order we compute the union. If you have a series of sets and you want to compute their union, you can do it in any order you like. So the set union operation can be generalized to as many sets as you like. You could take k sets S1, S2, S3 for any value of k and take their union. For example, we could define a set called cities in Asia. This would be the set of all cities in Asia, and we could create this set by taking the cities of every country in Asia. So you could define a set of cities of India, you could define another set of cities of China, you could define another set of cities of Japan, Nepal, Pakistan, Sri Lanka, Bangladesh and so on, all the countries in Asia individually. And then when you take the union of all these sets, you would get a larger set which would be the set of all cities in Asia.